So, welcome back. Next speaker for today is Professor Srikanth Iyengar from University of Utah, Salt Lake City, USA. He will be speaking on local cohomology and derived completions. Over to you.
Thank you. Yeah, so somehow the broad topic of the 4 lectures is dualities in local algebra. And I want to touch upon various topics, and they're not necessarily distributed according to the lectures. So the topics I would like to cover are cellular approximations, which, as you will see, perhaps not today, but in a couple of lectures, are very closely connected to what Somnath was talking about localization of spaces, but this will be on the algebraic side. And then there's also closely connected to this concept of cellular approximations is this idea of local cohomology, and this connected to derived completions. Then I want to talk about a class of Grothendieck rings that play a very special role when you're talking about dualities. And there is actually an analogous theory of Grothendieck spaces initiated by Felix Halperin and Thomas. If time permits, I will mention that. And that there's local duality, which is what makes Grothendieck ring special. Anyway, I'm getting ahead of myself by talking about these things. I'll bring them up by and by. So I did list a few references for my talks, and it occurred to me that there's one more reference that might be helpful, especially for the topologists in the audience. It's this survey article by John Greenlees, which is Homotopy invariant commutative algebra over fields. As you can see from the title, it's really connecting topology and algebra in a very intricate way. I should say that almost everything, my perspective on the subject and my presentation, etc., was strongly influenced by John Greenlees, not only through his writings. I was lucky to be his postdoc many years ago, and I learned much of this directly from him by word of mouth. Okay, so to get started, so yesterday, Samik began his lectures by saying that there is, in the last 70 years or so, so one is really interested in topological spaces. But in the last many years, this topologists have been working in this category of homotopy categories. So it's algebraic homotopy theory. And he made the point that one of the benefits of working in this larger category is that you can apply the ideas to various fields. And he didn't quite say it this way, but this has applications to algebra, to algebraic geometry, and these days even to number theory. Okay, and somehow the point of some of my lectures is that this also, working in this abstraction also has the benefit that you can transfer insight from any of these fields to algebraic homotopy theory, and then from there to the world of topology. And this happens in many guises. In fact, rational homotopy theory is one example of this phenomena, that you have certain ideas in algebra that you can lift to the world of algebraic homotopy theory, and therefore it has some relevance in topology. So even, for example, in specifically the world of rational homotopy theory, there are these ideas of depth that come up in local algebra that have turned out to be that you can think about in this broader world of algebraic homotopy theory, and then that is very pertinent to the study of topological spaces. But my lectures, and in fact the entire workshop, is somehow focused on a different aspect, namely duality, which there are aspects of duality in algebra and geometry, and once again you can formulate it properly. They make sense when applied to topological spaces. So this is really the theme of my lectures and overall of the workshop. But for today's lecture, I want to focus on a rather sort of simple or naive sounding problem. Let me state it like this. So the basic problem that I want to worry about is the following. So suppose C is any category. So you're interested in some category, perhaps it's of spaces, rational spaces, modules over some rings, whatever. And you fix an object, let me call it M, in this category. And you want to, so the questions that come up is, what are the objects? So what can you build out of M? What objects of C can be built out of M? Okay, of course, the word build, it has to be, so this depends on what category you're working with. So when I say build, you are only supposed to use the operations in this category. If you're just in the category of, or whatever category it is, it comes with certain operations that you can work with it, perform in it, and this building process out to use all these operations. And a closely connected question is, if you can't build, and more often than not, you're not likely to be able to build everything in the category from a single object. So the next thing you can ask is, given some object in the category, can we find best approximations? Can we approximate? Or look for, say, best approximations of A by M. Again, this is a very vague question, and this becomes more precise. And the way to make it precise is to work in some specific category and then ask about what approximations might mean and so on. And this is what I mean by cellular approximations, M cellular approximations. And so I want to take up this idea in the category of rings, modules over a ring. So that's the category I'll focus in. So today, so this is really where. So let me begin with a ring R. So the only thing I'll assume is that one belongs to R. I'm not making any assumptions on commutativity or associativity and so on. Oh, sorry, associative, yes, but not necessarily Noetherian or anything like that. So it's just a ring. And I'm going to be interested. So the category the objects I want to worry about, I could discuss this problem in the world of modules over the ring, but it turns out that that's sort of limited in scope. And you really bump into interesting phenomena when you work in the category of complexes. So let's say M and R. So M is an R complex. So instead of saying complexes of R modules, an R complex. So, and just to fix the notation and so on, for me, a complex is something that's indexed below. It has lower grading, and the differentials decrease the grading. So it's something like this. And I'm not making any assumptions about boundedness and things like that. So this is an R complex. And so you might think of this as the analogues of spaces. And then, so M is the analog for space. And then we have the suspension, which is the complex. So this is, which I'll talk of as the suspension of M. So it's a complex whose, so it's shifting this complex to the left by 1. So in the ith degree, this is mi minus 1, and the differential on this is minus the differential on M. Okay. So you get a new complex, as this is called a suspension of M. Well, these are the objects of a category, so which I'll call CR. So these are the objects of the category of R complexes. And the morphisms, or just say, yeah, I should say morphism, but I'll speak loosely of maps. So you have, so you map F from M to N, so you have a complex. So this is M. And this is then, if you have another complex N, So it consists of collections of maps which preserve degree. So this is fi plus 1, fi, fi minus 1, etc. And there are differentials here of m and n, and you want that these squares commute. So this is what the morphisms in this category are of complexes. Now, one is so the homology of M is the usual thing. So H of M, so I'll write H star of M for the total homology module of M, and I will not grade it. So I'll think of it as a collection of homology groups where HI of M is the ith homology. Just to set notation and so on. So this is, as usual, the cycles modulo the boundaries. Okay, and so this is what you might think of it as a total homology. So consisting of the homology groups, and for any map, so given map, so maybe I should be precise and not just say map morphism M to N, one gets a map from the total homology of M to the total homology of M. Okay, and we say that F is a quasi-isomorphism, and quasi-isomorphism if this map is bijective. What is an isomorphism? Of R modules, which is the same as saying it's bijective. And I'll denote quasi-isomorphisms by a tilde like this. Okay, so this you should think of as the algebraic version of weak equivalence. So you have a map between spaces and you're asking that it uses a bijection or isomorphism on pi star. And the category we're interested in, we wish to identify complexes that are quasi-isomorphic. So if you're interested in the category of complexes where you identify quasi-isomorphic complexes, and this is the derived category of R. And the usual problem that it's easy to define, but one doesn't know what one ends up with when defines it in this way. To get a concrete model for the derived category, one resorts to working with the analogues of CW complexes. So let me build it up with that. And the corresponding notion here, oh, by the way, there is an easier notion or a simpler notion to understand that's the notion of a homotopy equivalence. So you know what, one has also a notion of homotopy equivalence here. Of maps and and then one can so given there's a notion of given maps F and G from M to N, there's a of R complexes, there's a way to define what it means for these maps to be homotopic. So this will mean homotopic. Okay. I'll not bother recalling this definition. Most of you have probably seen this before. And this is an easier relation to understand than this of, okay, maybe I should. So this means maybe I should, because it's the first lecture, maybe I should be more precise. So we have two maps. So i.e. there exists, a map H from M to the negative suspension of N. So it consists of collections of maps HI from MI to, so these are not morphisms, just chain maps from N plus 1, such that, and the way I remember it is that D H minus D HDM is F minus G. Okay, so this is the usual notion of homotopy. Okay, and I'll write homs KMN to be the maps in the category of complexes, so morphisms M to N modulo the homotopy relation. So this is my definition.
So Srikanth, sorry to interrupt. There's a
Go
question, I think, in the chat.
Oh yeah, go ahead. I can't see the chat, so you should interrupt and let me know.
Yeah, would you like to ask, Parthapratim?
What was the question?
So it says, do the ring homomorph? Yeah, go ahead.
Do the ring homomorphisms preserve the identity?
Where are the ring homomorphisms?
Because you are taking your original category to be the category of rings, right?
No, I'm looking at fixing a ring and looking at complexes over that ring. I'm not even talking about change of rings here. Yeah.
Oh, okay. Just for a single ring.
Yeah. I'm fixing the ring.
Okay.
So this is fixed.
Okay,
I'm just looking at complexes over a fixed ring.
Okay.
And otherwise, of course, you want the ring homomorphism to fix the identity, but I'm not talking about change of rings yet.
Okay.
So everything is happening over a fixed ring. Okay. So as I was saying, there's a notion of the notion of homotopy equivalence of maps, which is, and then one knows, so, and if you have a maps and then we say that two complexes M and N, or if F from M to N is a homotopy equivalence, if it has an inverse up to homotopy. So if there exists G from M to N such that the usual thing, so as long as I get is homotopic, so this should, I've chosen a different thing. So this should be homotopic to the identity of M, and F compose G should be homotopic to the identity of M. And clearly homotopy equivalence implies, it's not hard to see that just by applying the homology functor to these identities. So homotopy equivalence implies quasi-isomorphism, but in general, the opposite, the converse implication is not true. All right, but this is, as usual, this is a much simpler equivalence relation to understand than homotopy equivalence is a much simpler relation to understand than being quasi-isomorphic. And the other, so the thing one has to introduce now is this notion of a semi-projective complex. Complexes. And this is going to be the analog of CW complexes in algebra. So a complex P is semi-projective, P in CR, or semi-projective. By the way, this terminology is by no means fixed. Different sources talk about different things, but let me just stick to this word semi-projective. If it has a filtration by subcomplexes, so you start somewhere, so this is 0. And then you have Pn and so forth, such that, so these are subcomplexes, so maybe I should say that. So, okay, 3 conditions. So everything is happening in P. So these are subcomplexes of Pn, of P. The second condition is that the union of these subcomplexes is P itself. And in some sense, the crucial condition is that the subquotients are the analog of spheres in algebra. So what should be are copies of R, but suspension. So I should say these are graded projectives. R is graded projective R module with 0 differential. with differential 0. So let me say a little bit about 3. So what is a graded projective? So as I said, what you really want is, so you know what a projective module is. It's a direct sum out of a pre-module. So Pn plus 1 over Pn is going to be of the form some sum of shifts of some, say, Qi, where the Qi are projective modules. And the condition that the differential be 0 is that Pn plus 1, the differential on Pn plus 1 lands in Pn. So you may think of going from Pn to Pn plus 1. So Pn plus 1 is obtained from Pn. By gluing free module or projective modules, graded projective module. I'll stop saying graded. So this is exactly as Samik explained, that a CW complex is obtained by gluing copies of the sphere, n cells in various degrees, and this is exactly the same construction. And these semi-projective complexes play the same role that CW complexes do in topology. So the crucial facts about this are the following. So the key facts, as far as we are concerned, is that they have the lifting property. So P semi-projective. And I'm going to quickly start abbreviating it as semi-projective, has the lifting property. So what I mean by this is that if you have a map of morphism of complexes, which is surjective, so that's analog of a fibration and a quasi-isomorphism, and given any map from P to N, you can lift it so that this triangle commutes. Okay, and the second condition is that if you're given, so from here, it follows that given M to N a quasi-isomorphism. So this is the same as saying that maybe this is not even condition 2. This is equivalently given this quasi-isomorphism. If you look at the map at the level of if you look at morphisms from at the level of homotopy classes, this is an isomorphism. Now, these are just abelian groups, by the way. There's no more structure here, so these are just abelian groups. So looking at maps from semi-projectives converts quasi-isomorphisms into isomorphisms. So that's the first thing. And from this, it's not so hard to prove that if P and Q are semi-projective, and you have a quasi-isomorphism between Q and P and Q, this implies that that quasi-isomorphism is actually a homotopy equivalence. This is a bit sloppy here. I'm saying that any quasi-isomorphism, F quasi-iso, implies F a homotopy equivalence. So in the world of semi-projective complexes, these two notions are the same. And the last thing is that any R complex, R complex N, has a semi-projective approximation as a map from M to P to M. This is a quasi-isomorphism. You can also choose this to be surjective. This is semi-projective. Okay, so this is the analog of every decent space having a CW approximation or something like that. Of course, the right context to discuss all these concepts is the world of model categories of one good context, and you'll hear more about this in Rekha's lecture tomorrow. I'm just taking a shortcut to okay. So once we have this, so it's not so hard given all this, it's not so hard to see that now if you look at these semi-projective complexes, so the category of semi-projective complexes, and so these are sitting inside the derived category of complexes. The semi-projective complexes modulo homotopy equivalence is this is an equivalence of categories. So this is D of R. So this is an equivalence of categories. So this is a good model for the derived category. Of R. Right. So for when I talk of some derived category of a ring, if you wish, you could think of as just that if I'm talking about semi-projectives modulo the usual homotopy relation. So for example, if I want to compute, one other thing I should mention in this context, you can even make a functorial choice so you can, at the homotopy level. So can make this functorial. So as I said, again, these are the sort of things that will get clarified when we discuss model categories. So let me write. So given our complexes, I will write Hom D Mn to be the morphisms in the derived category between M and N. From M to N. And the way to compute it is to replace M by a semi-projective resolution, which I may write Pm to N. And look at the homotopy classes of maps from Pm to N, where Pm to M is a semi-projective resolution. Okay, so this is how you compute morphisms in the derived category, and I will need a notation that I will write I want to look at maps not just from M to N, but from all suspensions. So this will be by definition I and Z. So this will be like the total, looking at all graded maps from M to morphisms from M to N. So this is just some notation. Okay, so this is then the category in which I want to talk about our cellular approximations, D of R. And the crucial thing about this is that this is a triangulated category. And the main thing, the main structure that's part of this is that there is a notion of a mapping cone. So given M and N, so given a map from M to N, so this is a map of our complexes. So this is a morphism. You can complete, so you can write down the mapping cone of this. So they'll write it as cone of F. We saw the topological version in Samik's talk. So this is the mapping cone construction. Cone of F. And then this maps on to the suspension of M and the suspension of N and so on. So this defines, these are the triangles. So these diagrams are the triangles in the derived category. So I may just usually just abbreviate it to this 4 terms or maybe even the first 3 terms. And just as in topology where Samik talked about these Barat-Puppe sequences, So the main outcome of this is that for any, say, P or W in the derived category, one has this triangle induces a long exact sequence. And then to the mapping cone and so on. And going up to so we have this longer exact sequence of abelian groups. Okay, so this is a very quick introduction to the construction of the derived category and also the triangulation of the derived category. So let's not get hung up about details. The main thing to remember is that the derived category has, it inherits taking direct sums from the category of complexes. You can take direct sums. You can also take direct products, which will come up later. It has suspensions. And the most important thing, it has this, it allows you to take mapping cones, which you should think of as the analog of gluing in the world of algebra. Okay, so with these notions, so these are the key operations in the derived category. So I can talk about this idea of building things in the derived category. So this brings me to sort of the second part. So fix now an M. So again, R is fixed. The ring is fixed, and you fix an M in the derived category. So you're just fixing an R complex. And I want to talk about things that you can build out of M. So I'll write thick M. So this is the thick subcategory generated by M. By M. And this is, so by definition, this is the objects that you can build, objects of dr that can be built out of M using the operations of dr. Out of M. And let me just say what these operations are. So first of all, you can take finite sums, and this is the finite part is what makes it thick rather than something else, finite sums. Then suspensions, of course, repeated suspensions, then mapping cones. So these are the operations in the derived category. And there's one more thing that comes up, and namely retracts or direct summands. So by which I mean, I should clarify what I mean. So if you have, say, if you have an X and there's a Y, which is a retract of X, let's say X is in this thick of M and Y is a retract, meaning that there are maps going in both ways such that GF is the identity of F in D of R, then Y is also in thick of M. So think direct summands. So you're allowed to take direct summands. Of objects in thick M, R in thick M. So it's closed under direct summands. Okay, so just again to emphasize, I'm just using all the operations that are allowed in the derived category, except that I'm sticking to this finiteness assumption here. So this is what defines thick M. And if I replace thick by, if I replace finite by allowing arbitrary sums, you get something called a loc of M, the localizing subcategory generated by M. Allow also arbitrary sums. So clearly, anything that you can build using finite sums, you can also build infinite sums, and so you have this inclusion. So I'll think of this as things finitely built from M, built from M, and these are just as things built from M. Okay, so these are two classes of objects that you can build from M. One is being finitely built, and the other one is being built. So we have to do an example at this point. The simplest object you can start with is when you take M equal to R itself. In this case, the thick of R is, these are complexes, this consists of complexes which are quasi-isomorphic to, so these are complexes. So basically isomorphic in dr to things of the form, say, like that, A, where, so it's a bounded complex, there are only finitely many non-zero terms, where each pi is a finitely generated projective. Okay, so this is sometimes called perfect complexes. I'll try not to use the term because perfect is loaded. In fact, from the topological or the categorical perspective, these are precisely the small objects in DR. Objects in DR, or compact objects. Small, or sometimes it's called compact. I'll use the word small, it's smaller. So what is a small object? So for any, let's say M in DR and collection of objects, so R complexes, Xi. So you can look at the maps from in the derived category from M to the direct sum of these complexes. And clearly the natural map from a complex to Xi to the direct sum gives you a morphism like this. And so you can take a sum outside. So M is small if this is a bijection for all families Xi. So this is a categorical notion. It's just using the intrinsic structure of DR as a category. So it's a important and useful result that these things that are built out of R are precisely the small object. So this requires some proof, by the way. So it's not a triviality. But it's not, given what I've said, it's not hard, but let me not go into it. So again, so recap is a thick of R, precisely the small objects in DR. This is E are the small objects in D of R. So this is about, so we know what things are built out of M. So this answers, remember I talked about this question that I want to think about, that in a category, given an object, what can I build out of it? So this gives you the answer in the derived category if we just start with a ring. Or at least finitely built are precisely the small object. And then the other point is that this is the localizing subcategory generated by R. So the things that you can build out of R are everything. So this is basically saying that, so this is equivalent to the statement that every complex has a semi-projective replacement. Okay, so everything can be built out of R in this. So that answers also the sort of the questions that I posed for M equal to R. And things get interesting when you start asking about different M. So what about a general M? Okay, so at this point, depending on who you ask, a topologist and algebraist, there's a result due to attributed either to Emmanuel Duar-Farjun or to Amnon Niemann. It says that there is, it's the following. What they proved is the following. So you look at the localizing subcategory. So I'm fixing M now, any object. Farjun was not working in the, neither Farjun nor Amnon were working. The derived categories are much more general, but this is what the result specializes to. So you're looking at the localizing subcategory generated by M as a subcategory of DR. And then the key point is that this has a right adjoint. Which I will denote cell M. So which I'll think of as a cellular approximation with respect to M, or M cellular approximation. Okay, so a right adjoint means that, i.e., for all X in DR, one has morphisms. There's a natural morphism from to X such that two things hold. First, this is M cellular, so in the sense that it is built out of M. And secondly, it's the largest thing that can be built out of M that approximates X for all, say, W. Actually, I don't even need to W. I can just say the following. Maybe I should say it like this. For all W and log M, the induced map to here this is bijection. So this is an isomorphism of abelian groups. So in fact, this is equivalent. This is not hard to see that this is equivalent to the following condition. That if you look at maps from M, this is an isomorphism, but you also want to worry about all suspensions. So that's why I introduced that notation there. So basically, as far as M is concerned, it doesn't see any more of X than this one. So this is why it's called the M cellular approximation of X. Did I say that? Yeah. And so it's basically the result says that the question I posed earlier has an answer in this context. Given any M, you can approximate, fix an M. Given any R complex X, you can approximate it using M in this way. There's a best approximation to X called the M cellular approximation. So this, by the way, this construction is closely connected to what Somnath was talking about localizations. And to bring up that point, one can do the following. So complete the map to a triangle. So I take the mapping cone of this map, and you get a functor from on dx, which I will call L for reasons I'll explain in a second. So you get a triangle like this, and the property about this map. So the key property about this object is that there are no maps from M. So this is 0. In fact, this condition is equivalent to this one. It's not hard to see from the long exact sequence, what I call the Bharat-Puppe sequence in this context. You'll see that this condition is the same as this. So you can think of Lm of x as, so this, we think of this as the M local object is M local or M trivial or M local. And to bring up a specific example, so if you look at, so R equal to Z, so you're looking at the derived category of Z. So we're just looking at abelian groups to some extent, or complexes of abelian groups, and you look at M is Z mod P, where P is a prime. Then Lm of any complex is just the localization, so you're inverting P. So this is how this construction connects with what Somnath was saying. So this, in fact, you can do it for also any collection of primes and so on, and you get the localization away from those collections of primes. So in Somnath's lecture, the focus was on this one, but I want to focus on this part of the story, the cellular approximation. Okay, so well and good. So what to sum up what I've been saying, in the derived category anyway, given any M, there are these cellular approximations. And I hope this simple example at least begins to tell you that this construction is worth looking at in general. But also in this specific case, it was rather simple. But in general, these objects are somehow quite difficult to understand what these M cellular approximations and M localizations are, or M trivializations are, except in one case, and that's when there's a very concrete description when M is a small object. So let me say this in general. Cell M and the cell, and therefore M, also Lm is sort of hard to get one hands on. How shall I say it? Is complicated is a good word, complicated. So I can't write down what it is explicitly, except when M is small. In the sense I've said before that it is finitely built out of M, R. And this is really coming to work of Dwyer and Greenlees. And before I do that, let me remind you of some classical ring theory called Morita theory. So this is classical Morita theory. So I think it's the fourth one. So it's and this goes back to the 40s, but there's a beautiful a survey or a beautiful summary of this work by Hyman Bass in his Oregon lecture notes. It's a very simple story, but it's actually remarkably powerful in the right gender. You know, it generalizes easily and it's remarkably powerful. So what it says is the following. So again, R is any ring. So you're fixing a ring R. And now you just fix a module, not just a complex, just a module. All right. And we want to understand what are the things built out of M, right? In this case, building just means taking direct sums and summands. And to that end, what you can do is look at the endomorphism ring of the module. So this is self maps of M. So this is viewed as a ring under composition in the usual way. All right. Now, then there is a functor from, well, there's a adjoint pair from R modules to E modules, but okay, well, for me, by the way, modules means left modules always. I should have said that before. So it's always left module. So EOP is the opposite ring. And there are two functors. So one is the one functor going this way assigns to an X the E module, the right E module on MX. So you see, M is naturally a left module over E. So when you look at maps into X, this becomes a right E module. So this is a right E module, which is why I wrote EOP. And they're given a right E module, why you send it to the functor y tensor M over E. So M is naturally a left E module. So these are the functors. So these are adjoint pair. This is an adjoint pair. And it induces an equivalence okay, so we had between, so we have from add of M to add of EOP, which are nothing but, oh, hang on a bit. I want to say not big add, but small add. So add of M to add of EOP. So what is this? This is the subcategory. So these are R modules that are direct summands of finite direct sums of E of M. And this is the same thing here, but of course, direct summands of E are just the direct sums, finite direct sums of E are the finitely generated free modules. And if you take direct summands, you get finitely generated projective modules. So these are finitely generated projective E modules. And so this functor, this adjoint pair restriction equivalence, actually, it's also worth writing down that, because they're an adjoint pair, you have maps like this for all X in R, you have a map E M to X, and also Y to sorry, this is the natural map goes this way, then Y tensor EM. And it's obvious, it's easy to see that, for example, this map is an isomorphism when you stick in X equal to M, and these are obviously additive functors. So this map will be an isomorphism. This is, I forget whether it's the unit or the co-unit of the adjunction. I guess it's the unit of the, I don't know, one of the two. This is the unit or the co-unit of the adjunction. This becomes an isomorphism on for X equal to M, and hence on any finite direct sum of copies of M, and it also then closed under direct summands. So this is very simple. If you just try and work through the details. So at the end of the day, what you get is that add of M is equivalent to this category of projective E modules. So this is a very useful trick which allows you to sort of convert any module into a projective module over some other ring. Now, you may wonder what this has to do with the approximation business, but if you do this in the context of the derived category, you end up with approximations as long as M is small. And the connection, I should make one more remark here and I'll stop. When M is finitely presented, and you'll finitely presented, we also get an equivalence at the level of the big categories, where you allow infinite direct sums. add of E of, which is just all projective E of modules. Okay, and what we are trying to do is find the derived, so the triangulated version analog of this construction in the triangulated category. So it's not surprising that classical Morita theory has something to say about that. So I'll stop here. I'll pick up on this theme next on my next lecture and explain how this can be adapted to construct good models for cellular approximations when M is small. So I'm going to stop here then.